Hi guys, so today we'll be solving this problem called minimum number of operation to sort a binary tree by level. In this problem, we've been given a root of a binary tree with unique values. In one operation, you can choose any two nodes at the same level and swap their values. Return the minimum number of operation needed to make the value at each level sorted in strictly increasing order. The level of a node is the number of edges along the path between it and the root node. So let's start and let's try to understand with an example. So first of all, we've been given the first example, 1, 4, 3, 7, and 6, and then 8, 5, and 9, and 10. Right. So in this problem, yeah, let's try to dive deep into it. So first of all, we need to return the minimum number of operation needed to make the values at each level sorted, right? So at this level, we have 4 and 3, and this level we have 7, 6, 8, 5, and this level we have 9 and 10. So 4 and 3, like we need to sort it out. So sort it out, which means like we'll need to swap 3 and 4 and 3, which becomes 3 and 4. So that's one operation, right? In this level, we have 7, 6, 8, 5. So 7, 6, 8, 5 need to be 5, 6, 7, 8, which means that it needs swapping with 5 and 7. So this becomes 7 and this becomes 5. And also these two. So this becomes 7 and this becomes 8. So it needs two swaps. 9 and 10 is already sorted, so we don't need to do anything, right? So yeah, total is 3, and that's what we are returning here. After this, we know that we got like we can do simple BFS traversal to get the level, to get the list of each level. From that list, what we can do is once we get the list, we can actually find the swapping needed for that list to make it sorted. How we can do it is so BFS is simple. The second would be like, operation. So first is BFS and the second logic would be for swapping, right? So how we'll swap is we can, so 5, 6, 7, 8. So we can maintain a 7, 7, 6, 8, 5, right? So 7, 6, 8, 5, 7, 6, 8, 5. So what we can do is we can maintain a sorted array and also the original array. So we'll sort out if we, because from the BFS we'll have the array ready and we can sort it out the array that has been given to us from BFS, and we'll maintain a sorted and a normal like the original array, and then we'll compare the position of each, right? 0, 1, 2, 3. We'll compare the position of each and see if if 5 is here in this position. If it's not, then what I'll do is I'll also maintain a map of, so 7 is at position 0, 6 is at position 1, 8 is at position 2, 5 is at position 3. So I'll maintain a map. So I'll say I need 5 to be here. So tell me what is the position at currently 5 is at. So 5 is at position 3, right? So what I'll do is we'll swap it out. We'll swap these two. So I'll say that, hey, 5, you need to be here. So swap the position of 5 to 0 and 7 to 3, right? And then also we'll actually go and swap this 5 and it will be 7, right? Then we'll keep on moving forward. So 6 is at 6th position. That's correct. 7 and 8, right? So 7 and 8 still, it's not there. So I'll go and find 7's position is 3, 8's position is 2. So I'll swap them out. So it will be 2 and here will be 3. And then I will also swap the original array. So this is 7 and this is 8, right? That would be the idea. Let's get to the coding part in order to understand a bit better. Let's get to the coding part. First of all, I'll maintain a queue is equal to the queue which will store the root, right? And then we'll also maintain the total swaps, which will basically be a variable which will count the entire swaps. So first of all, we'll do the BFS traversal, right? So BFS, we'll start with while queue is present, right? We'll have the level size is equal to length of queue and level val, which will store all the values on that level, right, in an array. And this will be passed to that minimum, swap required function that we'll be creating. So then for I in range level size, and node equal to q dot pop left and level val dot append node dot val. If node dot left is present, then we'll append the node dot left, and if node dot right is present, we'll append it to node dot right. Right, so that's the BFS traversal where we're popping out from the queue the leftmost value, and then we're appending it in the level value, which is the array, right? And then we just check the left and right. If it's present, then we push it in the queue. Once that's done, we'll call the total swaps will be updated. So total swaps will call the get minimum swaps function that will be creating, and we'll pass the level val inside that. And yeah, finally we'll return the total swaps, right? Once that's done, we'll have the get minimum swaps function, and here we'll have original array, right? So in this function, as I told you, I'll sort out the original array and I'll keep a targeted array, right? So sorted original, right? And I'll also need to maintain a variable swap0 to store the number of swaps required here. Yeah, so that's the idea. And as I said, I'll maintain a map of position to know like which position is currently at in the original array. So by the IDX, then I'll actually iterate through the original array, and we'll be checking if it's at original position is at the targeted array position or not. So if original of I is not equal to target of I, if that's the case, we know that we need to do a swap. So swaps +1, right? And then we'll get the current position from the position map, and currently wherever the original I is present, we'll store the current position, right? And also we'll make sure that we have sorted out, we have swapped it out. So the current position is equal to original of I, right? Okay, that's done, and then we'll just return the swaps from here. That would be the idea. Let's run the code to see if everything is working fine. Yeah, that works. Right. Cool. I hope you guys liked the video. Thank you.